Right over here is position, distance, displacement, speed, velocity, and acceleration. So we are going to start from the first one, which is our position. So from this position, what is position? Position is just the point in which an object can be found or located. You get? And this point, now we are talking about, this point is just how to, for us to locate this point, we have to locate it from its distance and direction from an already known point. That's how we can locate this point. And before we go about this, we will make use of our reference point, the reference point in which it has with this object and our point of origin. So let's quickly go over to our x and y coordinates, our coordinates of points, so it will enable us to understand this well. So this is our y coordinates, this is y and our x coordinates. This is our reference point, which is 0. Do you get? And this is our y, which is also known as coordinates. And this is our x, which is also known as our abscissa. Do you get? Okay. For us to complete this this drawing, you know, here is our positive y, and also here is our positive x. Down here is our negative y, and here is our negative x. So this is our coordinate point. So what if there is a point here? Let's know how to get points in different positions of this coordinate point. What if there is a point here? All we need to do is to trace that point to our x and y axis to know their coordinates, their x and y coordinates. So let's do the tracing. The trace is here. Let's say this point is our point A. This is point A. So how can we know the position of this point? It's just by getting the x axis, the x coordinates and the y coordinates. So let's say, assuming here is 2 and here is 3. Our x coordinate is just 2 and our y coordinate is positive 3. This is how to get the position of the point using this reference point and x and y coordinates. What if this point also appear here? Let's say here is point B. How can we get the position of this point? We are going to just do as normal, trace it to our y coordinates and trace it to our x coordinates. But if we check from this one, we first of all put our x coordinates before our y coordinates. Our x coordinate comes first before our y coordinate, which comes later. So here, assuming here is 2 and here is, let me say, 3. But if you check closely, here is negative x. So this got to be minus 3. So if we are going to take our position, the position of this point B, this is the x first, which is minus 3, comma, then 2 second. This is how to get the position of points in different plane. Okay, what if this point also appears somewhere here? All we need to do is trace and trace. Say this point is C. Let me say here is minus 2 and here is minus 1. This is minus, we pick x first, minus 2, comma, minus 1. This is how to get your position of points in different planes. You get? So let's quickly now jump over to distance and know how to get distance. Because from the word distance, this is just the gap between 2 points. Distance. Let me show you. Distance is just the gap between 2 points. What if a point was here initially, and this is point A, and this point later moved on to a new point, which is point B. It now moved on to a new point. This is point B. And the gap between them is 50 meters. It now moves a space of 50 meters to another new point. So we can say that the distance between this point A and point B is that the distance is equal to 50 meters. But what if this object moves from here to here and we don't know the space between them? We don't know the distance they have moved. Do you get? What if we only know their coordinates? Or let me just quickly bring it into our coordinates of points. These are coordinates. What if an object was here initially and it now moves here? This is point A, this is our point B. We don't know the distance, but we know our coordinate. Let's say here is 2, 3, and here is 7, 10. This is the coordinate of B. This is the coordinate of B, this is the coordinate of A, but we don't know the distance, we don't know the gap between it. We term it S, or maybe AB. When we use AB, we don't know the gap between them. All we got to do is what? Let's come over here and solve. So let's check what we do to this stuff. All we got to do is AB squared. Let's find our distance between this A and B. This is AB squared is equal to X. We're going to start with our X. That is X2 minus X1 squared plus our Y2 minus Y1 all squared. All squared. This is how to find the coordinates. This is how to find the distance of 2 points. When you don't know the distance, but you know the coordinates, you know the X and Y coordinates. So let's quickly go over from this and find our distance. So that our AB now will be square root of our X2 is what? We normally know that the first one, this is X1, this is X1, and this is Y1. This is the first one, and this is our 2. This is our X2, and this is our Y2. So from here, we can quickly go over and solve this example. Because our X2 is 7. That is 7 minus our X1 is 2. All squared plus our Y2 is 10 minus our Y1 is 3. All squared. So 7 minus 2 is just 5. Our AB now should be equal to square root of 7 minus 2 is 5 squared plus 10 minus 3 is 7 squared. So AB is now equal to square root of, this is 25 plus our 49. The square root of 749, square root of 5 is 25. And finally, our AB is now equal to the square root 9 plus 5, this will give us 14. We write 4, carry 1, put here 3 plus 4, 74. So finally, the square root of my calculator, that is the square root of 74, will give us 8.6. That is 8.6. Our AB is now equal to 8.6 meters. This is how to find the distance, or let me say the distance of 2 points when you don't know the distance. Do you get me? But you only know your coordinates. Okay, let's now quickly move over to displacement. Displacement, which is this, is just distance traveled in a specified direction. You get displacement, distance traveled in a specified direction. So when we are talking about distance, we are not interested in the direction it is. We are just interested in what distance does it cover when you move from here to here. But when we talk about displacement, we are talking about distance we covered, but the direction. So what if, let me say, example of this distance, we can say that a man traveled 30 kilometers east. Let me say 30 kilometers east. This east now is signifying or is showing you the direction of the man. Let me say the direction in which the man traveled to. That is this east. You get, a man can also travel 50 kilometers east, north, west, anything, but the direction must be indicated. But in this distance, all you got to hear is 30 meters, 40 kilometers, no direction. So what if a man travels, let me say 20 kilometers east? Let me say a man starting from point A, this is point A, he travels 20 kilometers east. But on his way as he was traveling, he just forgot something at home. He remembered, oh, I forgot something at home, and he started coming back. On reaching here, he thought, in fact, I have what I thought I forgot at home. And he now stood in this position. And when he turned back, he walked a distance of 10 kilometers. 10 kilometers west. Then, if you are asked to find the displacement of this man, remember, if you are asked to find the distance of this man, I just want to digress a little. If you are asked to find the distance of this man is just 20 plus 10. The distance, which is S, is equal to what? 20 plus 10. 10 kilometers. Sorry. 10 kilometers. plus 10, which will give us 30 kilometers. But when we are talking about displacement, the displacement of this man from here to here, we don't want to know how far the man has traveled. We want to know the nearest point in which we can get this man. That is, the displacement will be from here to this place in which the man is, which is 20 minus 10. The displacement is just 10 kilometers. Another illustration we can use to understand this displacement better is when a man travels, let's say a man starting from this point A, he travels 40 kilometers east again. Let me say he travels 40 kilometers. This is 40 kilometers east. And from here he travels 30 kilometers north. He travels 30 kilometers north. This is 30 kilometers. And we're asked, this is our point B. And we're asked to find the displacement of this man. All you got to do is complete this line from here to here and use our Pythagoras theory to get our displacement. But although if you are asked to find the direction or the distance, the distance is just 40 plus 30, it will give you 70. But when you're asked to find the displacement, that is the nearest point in which you can locate that man. And the nearest point is from here to this point B. And if we use our Pythagoras theory, it says also that x squared is equal to 40 squared plus 30 squared. So that our x will be equal to the square root of 40 squared plus 30 squared. So that our x should be equal to, if you solve this out, you get that our x is 50 kilometers. 50 kilometers, and this is north east. 50 kilometers north east. This is how to find the displacement, and once you find the displacement, you show the direction in which your displacement goes. But assuming it is distance, it is just 40 plus 30, no displacement. Okay, let's now quickly go over to speed and know how to do our analytical calculation on speed. Right over here is speed, and as we know from our formula, speed is just the rate of change of distance. The rate of change of this distance, and it is denoted by the letter V, which is equals to distance. This is distance S all over our time, which is measured also in seconds. Okay? And if you look closely, speed is distance over time, and distance is a scalar quantity. Therefore, speed is also a scalar quantity. Okay, what if a body of mass, which is A, moves from this place now to another place with a speed of 20 meters? A speed of 20 meters. It covers this distance with a speed of 20 meters in 2 seconds. If you are asked to find the velocity of this body, you will see that velocity is just distance over time, and our distance is equal to, and our velocity and our speed will now be 20 meters over 2 seconds, which will give us 10 meters per second. This will be our answer. But what if this body again move from B to another position, C? This is B. It moves from here to another place, which is C. Okay, and it moves a distance of 20 meters again with 2 seconds. If you watch, it is moving with equal distance, with equal time interval, and this is what we call uniform speed. Uniform. This is what we call uniform speed. And again, the graph of this uniform speed. This uniform speed have a graph of this. This is our distance, which is S, our distance, and here is our time, which is measured in seconds. Our distance is meter, and this is the graph of our uniform speed. Do you get? But again, what if a body moving with this uniform speed around a roundabout, or maybe in a circular path? It will be very difficult for us to calculate the exact speed of any moving object in a circular path. Therefore, That is what bring about what we call our average speed. This average speed is the total distance covered over total time. When it is difficult for you to calculate the speed of anything moving in a circular path, this is equal to our total distance all over total time. Okay? Therefore, let's now quickly go over to velocity. And as we know, velocity is just the rate of change of displacement over time. Velocity is simply displacement over time. So our velocity, which is v, is now equal to displacement, which is s, all over time. This is our displacement measured in meter, and this is our time measured in seconds. And if you check velocity, displacement is a vector quantity, then velocity is also a vector quantity. Okay? Therefore, the same thing that is applicable to this speed is also applicable to the distance. But speed is distance over time. It deals with only distance, no direction, but velocity goes with direction. You get? That's why velocity is a vector quantity and speed is a scalar quantity. Again, when a body from A moves to point B with a displacement of, let me say, 30 meters under 3 seconds, you get? If you are asked to find the velocity of this object, the velocity v will now be our displacement. This is our displacement, 30 meters all over 3 seconds. And it will give us 10 meters per second. Okay? And if this body again moves from here to another point C with equal displacement and equal time and equal interval of time, this is what we call also uniform velocity. Okay? Uniform velocity. And again, the graph of uniform velocity goes like this. This is the graph of uniform velocity. It goes like this. Although velocity is displacement, here will be our displacement. Displacement, and here will be time, which is in seconds. Displacement is in meters. What if the velocity we just treated now, this our velocity? What if this graph of our displacement over time, what if it is not uniform? What if it is not, we don't have a uniform velocity? What if we have a graph of, what if our graph is something like this? It goes like this, and here is point A, and here is point A, and here is our displacement, and here is our time again. And they ask us to find the velocity at A. And if you watch now, this is not as this, which is a uniform velocity. Therefore, this is, to find the velocity of A, we have to find the velocity at this instant, this particular instant. And this is what we call instantaneous velocity. A velocity at A instant. It is called instantaneous. Instantaneous velocity. This is the velocity at every instant. We can also find the velocity here. We can also find the velocity here. It is the velocity at every or any instant. Let's quickly go over to acceleration before we come to velocity time graph. We will make all this thing more easier when we go over to our velocity time graph. Here is our acceleration. As we know, acceleration is just the rate of change of velocity. Our acceleration, which is this, is the rate of change of velocity, which is v minus u all over time. And this our v here, this capital V is our final velocity. This is final velocity. This our u is our initial velocity. And this t is our time. Okay? So this is the increase, acceleration is the increase in velocity with time. But how about retardation or deceleration? Retardation is the decrease of velocity with time. Okay, let's go over to their graph. The graph of acceleration goes like this. The graph of acceleration, this is the velocity. which is meter per second, and this is our time. When a body is moving with a constant velocity with equal time interval, let me say when a body is moving with a constant velocity, let me say 20 meters per second, and another 20 meters per second, in equal amount of time, this is what we call uniform acceleration. Let me say a body moves from point A to point B with a velocity of 20 meters per second in 2 seconds. Do you get? I move from this point B to another point C in the same 20 meters per second within 2 seconds. This is what we call uniform acceleration. And the graph of uniform acceleration is drawn like this. This is the graph of our uniformly acceleration. This is uniform acceleration. Uniform acceleration. This is our graph of uniform acceleration. How about retardation? When a body is uniformly retarded or decelerated. When a body now moving, or let me say decreasing in each velocity in equal amounts with equal time interval, this is what we call uniform retardation or deceleration, and it has a graph of this. This is the graph. Here is our time. Here is our meter per second, which is our velocity, and here this is the graph of uniform retardation. Uniform retardation or deceleration. Okay, so from here, let's quickly go over to velocity time graph and analyze everything. From that velocity time graph, this acceleration, velocity, speed, it will give us a rapt understanding. It will expose everything we need to know about all these things we are solving now. Okay, over here is our velocity time graph. I told you before that from this velocity time graph, we can study all these acceleration, velocity, speed, retardation, distance. It will enable us to understand every atom of it. And right here is a question that can enable us to understand velocity time graph in detail. Okay, and the question says that a car starting from rest accelerates uniformly and attains a speed of 80 meters per second in 30 seconds. It maintains this steady speed for another 30 seconds. It then slows down uniformly until it comes to rest in the next 40 seconds. Sketch the velocity time graph for the motion of this car. Obtain from the graph the uniform acceleration during the first stage of the journey and the retardation during the last stage of the journey. For how long did the car travel altogether, and what is the total distance covered by the car? This question, I just want to, from this question, let's go over to our table of value. From the table of value, we'll go over to our graph. I normally come across questions with table of values only, but I know if you start from that table of value, you won't understand this one. Let me from here go over to our table of value. I will transform all this into table of value. From there, we'll go over to our velocity time graph, and from there we'll go into solving. Okay, so our table of value says the upper one is, let me say, this is velocity, which is meter per second, and below is our time. Okay. This is our table of value. So here is solution. Here is solution. They said a car starting from rest. Once we hear a car starting from rest, that means the initial velocity is what? 0. And the initial time is 0. So the first thing in our graph is 0.0, and here will be 0 time. Okay, a car starting from rest accelerates uniformly and attains a speed of 80 meters per second. Okay, it now attains a speed of 80. This is 80 meters per second in 30 seconds. Here is our time, 30 seconds, and time is in seconds. Okay, it maintains this steady speed for another 30 seconds. Okay, it maintained that steady speed. The speed did not decrease or increase. So here is our another 80 meter per second. For another what? For another 30 seconds. The first one is 30 seconds. So the second one now is 30 seconds plus second 30 seconds, which will give us 60 seconds. Because the first is 30 seconds. It maintains the speed for another 30 seconds. So the total is now 60 seconds. Okay? It comes for another 30 seconds. It then slows down uniformly until it comes to rest in the next 40 seconds. You get? It now do what? Where is it again? It then slows down uniformly until it comes to it comes to rest in the next 40 seconds. So the total time now, the 40 seconds plus this 60 is 100. So it slows down uniformly until it comes to rest. Thereby, here is 0. It has come to rest. It slows down uniformly to rest, and it comes to rest at the time of under 40 seconds, which makes our total time to be 100. The first time here is 30. The second time is 30, which is this 60, and the last time is 40, which is this 100. And by 40, the car has slowed down. It slows down uniformly to rest. Thereby, our velocity is now 0. Okay. From here, this is our table of value. This is our table of value. It now asks us to obtain from the graph the uniform acceleration during the first stage, the uniform acceleration. So I question is uniform acceleration from the first stage. The II of the question says for the motion of this car, okay, obtain from the graph the uniform acceleration during the first stage of the journey and the retardation during the last stage. The retardation last stage. During the last stage of the journey, the III is how long did the car travel altogether? III is total time. How long the car travel altogether? Then our IV is what? The total distance covered. That is total distance. Total distance. I just converted all this grammar into a simple form that everyone can understand. Okay, from here now, all I need is just this, my table of value, and this to solve all this problem. We can simply go ahead and clean our question. You can go ahead and clean our question. This is our solution. Okay, the first is uniform acceleration from the first stage. First of all, let's draw our velocity time graph. And this is our velocity time graph. Here is our time in second. And here is our velocity, our V, in meter per second. Okay? So the first, they started from rest, which is here. Two of them started from rest. And the velocity now increased to 80. Let's say here is 20 velocity, here is 40, here is 60, here is 80. Okay? And they increase to 80, 30. Let's say here is 30 seconds, here is 60 seconds, and here is 100 seconds. Okay? This is our time. Okay. It moves from here to here at the first stage. Then it maintains this velocity for another 30 seconds. So it maintains this velocity here for another 30 seconds. Do you see? And from this velocity, from this 80 meter per second, it now decreased to 0 from here it now decreased to 0 at 100 seconds. This is our velocity time graph. Okay, from here now we have successfully drawn our velocity time graph. Let's go over and answer the uniform and answer our I question, which is uniform acceleration from the first stage. The uniform acceleration, this is the first stage from, let's say here is A, here is B, here is C, here is D. Our uniform acceleration from the first stage is our AB. Okay, and we know that acceleration, which is A, this is I, is equal to velocity, change in velocity over time. Change in velocity over time. So how do we go about and get our velocity? From here, from this point to this point, our velocity now, because we are in a velocity time graph, our velocity will be final velocity. Here it has a final velocity of 80 minus our initial velocity. Initial velocity is 0, which is here. Our final velocity, which is 80 minus initial velocity. So this is our V2 minus V1 all over our T2 final time minus initial time. And our final time is 30, initial time is 0. So from here, we'll go over that. We'll derive that acceleration is V2. From here, our V2 is 80 minus 0 over 30 minus 0. So that our final acceleration will now be 80 over 30. If you cancel out, this is 8 over 3. This is 8 over 3, which is 2 points. Let me punch in a calculator. This is 8 divided by 3, which is 2.67. Which is 2.67 meters per second squared. This is our acceleration. Next is the retardation at the last stage. The retardation at the last stage. The last stage is from this. This is where we have retardation from here to here. We're also going to find our retardation, which is negative acceleration. Okay, our retardation is this. The same way we did for acceleration, we are going to repeat the process for our retardation. So retardation is the same thing. Retardation, negative acceleration is equal to the same V2 minus V1 all over T2 minus T1. And this will give us, let me clean this minus sign. And this will give us our V1 from here. Our final velocity from this retardation is 80 minus our final velocity. This retardation starts from this C and ends here. So our final velocity is this, our 0 here, and our initial velocity is this. In this one, this is our initial velocity, this is our final velocity. It goes like this, and from here it goes like this. So here, this is our initial velocity, and this is our final velocity. So final velocity, which is 0, minus our initial velocity, which is 80. So retardation will be 0 minus 80 all over our T2, which is our T2. Our T2 is 100. 100 minus the time in which our initial time is at this point C, which is 60, and our final time is at 100. So our final time is 100 minus 60. This will give us 100 minus 60. Okay, so let me clean again. Our retardation will now be 80 minus 80 all over 100 minus 60 is 40. This will give us minus 2. This is our retardation. Then the III question says that we should find the total time, and the total time for this car, the total time it takes this our car to start from this A and ends in this D is 100. That is the first 30, you know, here is 30, the second 30, and 40. So our total time is 30 plus 30 plus 40, which we just did when we were solving the question, which is 100 seconds. 100 seconds. And our final question is the distance covered, the total distance covered from here to here. So I can clean the board now so that we can find the distance. Our distance covered from here to here is question IV, total distance. Our total distance is just the sum of the areas of this shape. We have three shapes. This first shape is triangle, this second shape is rectangle, this third shape is triangle. The sum of these three shapes will give us the total distance that it takes from A to B to C to D. So our total distance is the area of, this is triangle, area of triangle A, B, let's say here is I and here is II. ABI, area of triangle ABI plus area, here is rectangle, rectangle IBCII. This is area of rectangle, IB CII plus area of this final triangle, area of triangle, this is triangle IICD. Do you get? So the total distance is just area plus area plus area. When you sum the three areas, an area of the first triangle is half base times height. So the first area here is half base times height. Our base is 30, our height is 80. So this is half, area of the first triangle is half times our base is 30. Half 30 times our height is 80, because the height starts from here and reaches here. That is 80. Okay. Plus the second area is area for this rectangle. And area for rectangle is just base times height. So our base is 30 times height, which is also 80. 30 times 80 plus, and our final triangle, which is half base times height. Let's write here, half, our base is 40 times our height, which is 80. Times our height, which is 80. So if we solve out, this is 2 into 30 will give us 15. 15 times 80, 15 by 80 will give us 1.2 times 10 raised to power minus power 3 plus 30 times 80. 30 times 80 will give us 2.4 times 10 raised to power 3. And here 2 go here, 2 go here, it will be 20. 20 times 80, 20 times 80, it will give us 1.6 times 10 raised to power 3. And if you add all together, this is 1.2 plus 2.4 plus 1.6. 1.2 plus 2.4 plus 1.6. This will give us 5. Our total distance will be 5.2 times 10 raised to power 3 meters. This is our total distance it takes to cover from A, B, C to D. Okay, there's a very easy way of finding this total distance. If you don't want to go through all this rigorous calculation, the total distance is all about areas of shape. If you check the area of all this shape together, you will see it is a trapezium. You can simply go ahead and find the area of this trapezium and get your answer once. Let's solve it here. Let's do our alternative here and get the same answer as we got there. So area of a trapezium is just half AB times height. Half, this is our AB is the two adjacent sides. Half AB times height, which is two adjacent sides. The first adjacent side is this side, and the second is up here, times our total height. So if you go straight and say that this is half into our A is distance from here to here, which is 100, plus our B, which is here to here, which is 30, times our height, which is 80, the height of this trapezium. If you go ahead and solve, this is 100 plus 30, will give us 130 divided by 2, 130 divided by 2, times by our 80. It will still give us the same answer, which is equal to 5.3 times 10 raised to power 3 meters. This is our final total distance, sorry, 5.2. 5.2, and if you check, we got the same answer. So there are two methods of finding this total distance, and distance is all about knowing the area of the shape formed while finding your velocity time graph. And if you also look here, let me just digress a little. We have finally gotten our answer, so I just want to go a little more to show you something. Along here is where we have our uniform velocity. If you watch here now, this is where we have uniform velocity. And if you check from that the graph of uniform velocity, it goes like this. And if you also combine it with this, you see that this is our uniform velocity. But what if here that is our uniform velocity is not straight? Let me wipe. Please, I don't want to confuse you. I just want to show you a small thing that this question doesn't cover, which is the area of instantaneous velocity when this place is not uniform. From this question, we have a uniform velocity. What if this graph goes like this? What if this graph goes like this? That's what I want to show you. Here is now our instantaneous velocity. Do you get? Or where we have variable acceleration, where our acceleration varies. Do you get? How do we go about to find this instantaneous velocity, or in terms of acceleration, variable acceleration? All you got to do is just draw a straight line from here and cut this. Once you draw this straight line, complete this your line like this. Do you get? And from here you can find your your instantaneous velocity or variable acceleration at this point C. So if here is, let me say here is 80 and here is 20 and here is 30 seconds and here is 70 seconds. All you got to do if you want to find your velocity or your acceleration from this is 80, this is 20, this is 30, this is 70. Do you get? Therefore, your acceleration now will be, this our V, this our final V minus our initial V, that is 80 minus 20 all over 70 minus 30. And 80 over 20, our acceleration will be 80 over 20 will give us 60. 80 over 20 is 60 over 40. If you cancel 2 here, 2 here, 3. So our acceleration will be 3 over 2. Or 1 whole number, 1 over 2. Meter per second squared. Meter per second squared. Okay, I just digressed a little to show you when we have variable acceleration or instantaneous velocity at this point. You get? So let's now go over to our motion. Let's find our uniformly accelerated motion or linear motion. Do you get? Equation of motion. Let's go over there now.